So you should feel comfortable doing the third assignment as well, okay, before your exam. And for these first two assignments, I will post the solution also. I'll scan the solution and post it by this weekend. So in the last lecture, we looked at the so-called impulsively started flow. Basically a flow which is initially stagnant and all of a sudden you are imposing a pulse motion, okay, the motion that starts suddenly. And we should be able to simplify the Navier-Stokes equation under those assumptions and show that it simplifies to that equation that you have there. And the solution to that bisimilarity transformation in the situation where you have a semi-infinite geometry is given by the error function. Okay, and then we saw a variation on that where the plate, a second plate, is placed at a finite distance d, and when that happens, we saw that the solution is obtained only through a separation of variables, and it is an exponentially decaying part until it reaches the steady state, and that solution is also analytically given. Now there are lots of variations on this. There is a book by Korsla and Jaeger called Conduction of Heat in Solids, and the entire book is devoted to solutions of equations of this type that you see there. This is a linear equation, so there are many variations you can look at, initial conditions, boundary conditions, geometry, and all of them are amenable to solution by analytical methods. And the techniques essentially are variations of the techniques that we have seen. Okay, so in Cartesian frame it will be Fourier series, but if you go into cylindrical frame it will be Bessel functions. If you go to spherical frame, maybe it's spherical harmonics. So these are all basically infinite series solutions. So the idea essentially remains the same. And those who have not seen separation of variables, you should make an effort to look at a few more examples, particularly looking at orthogonality of properties and functions, stuff like that. Now, today I want to do one more variation on that sequence of problem where, once again, we are going back to that infinitely long plate. So the situation is that you have a plate that is moving with the velocity of u at the bottom, and in the normal direction, the fluid is spanning the entire infinite domain. But the variation is the plate now is not moving with a steady velocity u, but it is oscillating with a certain velocity that is given to you. Okay, and so one of the boundary condition changes, and that boundary condition is the horizontal velocity Vx at y equal to 0, that is at the bottom plate, is a function of time. It's not a constant anymore, it's a function of time, and it's a periodic function of time. So the maximum velocity that it can reach is u, but it will oscillate. So if you plot that particular profile, what you will find is at the bottom boundary, Vx at y equal to 0 for all time, you find it as cosine, like that. It just goes on forever. Okay. Intuitively, what would you expect when such a boundary condition is imposed on the problem that we have already talked about? We know the solution when it is uniformly moving, which is the error function. Okay, so how does this problem differ? I'm not talking about mathematically, but intuitively from your physical understanding of the flow. Would you like to make any observations, comments on what you expect such flows to be? It is clearly from 0 velocity, it is accelerating. Okay, so once again, if I draw this profile, it's something like this. So there are parts of the region where the velocity is increasing, it's accelerating, and there are parts where it is decelerating, in the sense it's going back. Okay, and I'm going to look at the behavior not on the short time scale. That is, initially it is at 0, and when I start oscillating it, this is going to evolve from 0 velocity to some sort of quasi-periodic velocity profile. Okay, that's the first thing that I expect intuitively. I'm imposing an oscillation. So what do you expect if I put a red dot somewhere here? What do I expect the red dot to be doing? Will it be stagnant? It will move to the right for a while, and then it will move to the left and right and left and right. Okay, so initially it will take some sort of a transient path towards that periodic profile. Okay, so in the long time, there is no steady state again. It will reach, every point will reach its own periodic oscillation. What would be the amplitude of the oscillation close to the plate? The amplitude, maximum u. Okay, so it will go from plus u to minus u. Okay, so that is the maximum extent with which the velocity will change from from maximum u to 0 to minimum negative u in the opposite direction, comes back 0, and so it continuously accelerates. Okay, you can look at it acceleration or deceleration, which is acceleration in the other direction. Okay. So if I plot the velocity profile at any one of these points, I'm going to get a periodic solution with a different amplitude, perhaps. Depends on how far away I am from the plate. Okay. So what you see here in this picture are some of the velocity profiles. Okay, there is one there. There is one at another instant of time. Okay, previously at various instants of time we got a self-similar profile. Now there is no self-similarity. Why? What did we see about requirement for self-similarity? You should be able to combine the three variables that are left in the problem, that is y, t, and nu, into a dimensionless group. Then you can define a new variable, and the function, the unknown velocity, will be a function of that single variable. But in this case, I have another parameter that is given to me, that is omega. What is omega? Omega is the frequency of oscillation. How fast? Is it moving slowly or is it moving very fast? If omega is high, that means a very high frequency oscillation. If omega is very slow, that means it's a low frequency oscillation. Okay, so that is a parameter I need to decide, because when I am hooking up to a motor to move the plate, I set the frequency, so I can adjust it. So that's a control parameter that I'm imposing on the problem. So in addition to y and nu and t, I have a fourth parameter in the problem, which is omega. What is the units of omega? Radians per second. Okay, so it's 1 over second. So it has the units of second. So there is a natural time scale in the problem. Okay, so we can achieve a similarity transformation only when there is no natural length scale or no natural time scale, and the three variables can be combined into a single variable. So in this problem again, there is no, there is a natural time scale, so there is no similarity transformation. So we have to use separation of variables idea. Okay, but to answer the question, what is the long-term behavior of the velocity profile at any point? What I want to be able to do is predict the velocity profile at any point in this domain over a long period, not from the time when I start. And that long-term behavior is going to be also periodic. So I'm proposing, this is a postulate. One postulate the solution of the form that the velocity in the x direction is going to be a function of e to the power I omega t times a function which is a function only of y. That is the idea behind separation of variables. In separation of variables, what did we do? We wrote this function as a function which is a function of time and another function which is a function of y. Here we are not only saying that, we are also saying that the function in time has a very specific form, because I expect the solution to be of that form, that is periodic. Okay, so I'm saying that the function is going to be equal to e to the power I omega t. Do you know what e to the power I omega t is? It's cos and sine, cos omega t plus I sine omega t. Something called the Mobius Theorem that allows you to write e to the power I something. E to the power I theta is cos theta plus I sine theta. These are the kind of formula that I will put in the formula sheet, but if anything that is not there that you think you need, you are welcome to write them down on the space that I provide. Okay, so we are proposing a very specific form that it's made up, the solution in time is made up of only sines and cosines. That idea comes from the fact that the problem is forced with a frequency which is cos and sine. Okay? So whenever that happens, you can always construct a solution of this form. Now, in the book by Kundu, this problem I think is not handled in Burstewar and Lightfoot, but it is taken from Kundu. He shows you how to develop this using the separation of variables. That I do want you to be able to take care of, because there are exercise problems in Burstewar and Lightfoot that also take you through a very similar step in a rotating concentric cylinders, which are used in viscometers. Okay, the same idea. Now, what you would have to do at this stage is take this velocity profile that is proposed, plug it back into the original differential equation, and you will find that you will get a single ordinary differential equation in the unknown f of y. So you'll get an f double prime y, and the derivative with respect to time you can actually explicitly take them because you know what the function is. Okay, so you'll get a single ordinary differential equation subject to the two boundary conditions. Okay, and those boundary conditions will have to impose. Eventually, you will get the solution for the velocity in the x direction. So that consists of e to the power minus y square root of omega over 2 nu cos omega t minus y times square root of omega over 2 nu. That is the analytical solution. You can very easily verify at this stage. This kind of thing I may ask you to do in an exam. Okay, so I've formulated the problem and then I say show it to be the solution to be like this. Okay, and so you should be able to take that, plug it into the differential equation, get a second order ordinary differential equation with a constant coefficient, solve it, and show it to be this. And then I would ask you questions on that profile. Let me ask you those questions. Okay, what do you see about the nature of the profile in the y direction, in the direction perpendicular to the plate? It's an exponentially decaying function. As y increases, you see y here. As y increases, you have e to the power minus y. Okay, so it decreases. Okay, which is the same thing that we also saw in the similarity transformation variable, that it will no, it's not, because there it will continue to propagate all the way to infinity. But here we have an exponentially decaying in space, whereas in the finite plate we saw an exponentially decaying solution in time. Okay, so this is an important observation that you need to make. Why? Because this tells us that the momentum diffusion that is caused by the moving plate is not felt all the way up to infinity, because this function will be driven to zero. It depends on the frequency, it depends on the viscosity, kinematic viscosity of the fluid, but for a given frequency and a given viscosity, there is a finite position y by which that function will be driven to zero. It could be near or it could be far. That depends on what is the value of omega, what is the value of nu is. Okay, so a distinct behavior of the solution is that the oscillation of the plate is not felt throughout in the entire domain. It felt only over a finite domain. Why does that happen physically, intuitively? Exactly. Do you remember, again, this goes back to the movie that I asked you to see. How many of you have seen Taylor's movie yet? I have to give some extra credit for those who have seen it, or penalty for those who haven't seen it. So there you have this rotating cylinder, right? And there is a dot that he places, and he rotates and sends it, takes it back, and you find that the dot reappears in its original position. He calls that as a kinematic reversibility. Okay, so here that's basically what is happening. When the plate is moving forward, it sets up all the fluid layers close to that plate in the forward direction. So any dot that you put in will start moving in the forward direction, and then it reaches the maximum velocity u, starts going back, and so all the fluids will start retracting. Okay, so every dot that you place on that fluid element will traverse only in this direction, back and forth. And as you go farther and farther away, the extent of the amplitude will become smaller and smaller. So if you take a point from here, for example, it sees very little oscillation. Okay, a point here might see a much larger oscillation. The point here, you see an oscillation like this, whereas this is the maximum oscillation that you can have, from -1 to +1, minus u to plus u. Okay, so because of the shear stress reversal, the flow reversal itself, it cancels. So the momentum diffusion is going forward for a while and then it's going backward. Okay, so it doesn't have, you're not continuously adding momentum transfer diffusion in one direction, like you would do when you're moving the plate in the same direction. That diffusion can go all the way to infinity. But in this case, because there is a reversal, there is a finite distance by which the flow will penetrate, and beyond that the fluid does not know that there is a plate and the plate is oscillating. Okay, and I can ask you to find what the distance is for a given fluid at a given frequency. You should be able to do those kinds of analysis given the solution. Any question? Is it clear or not? Yeah. How did I get this velocity profile?
Yeah.
I guess this velocity profile.
Yeah.
What is the equation that I am solving? The equation that I am solving is dvx dt equals mu p square px dy. It's the same equation. Okay, and the only thing that is changing is the position. So what I need to do is I need to take this velocity profile and plug it in there. Okay, so when you do that, for example, on the left hand side, what will you get? You will have to take the derivative of that function with respect to time. So it will be derivative of e to the power anything is what? Same e to the power omega t times I omega. Okay, times what? And then you will have the f of y. You don't take derivative because it's a partial derivative, right? So it will be simply f of y. F of y times the partial derivative of, I'm taking the derivative of plugging it in here. Okay, so I'm taking the derivative of this entire thing, but f of y is independent of time, so that stays as it is, and take the derivative of this with respect to time, which will give you e to the power I omega t times I omega. Okay, and then on the right hand side we will have nu times the second derivative of this with respect to y. So in that one, you will simply have e to the power I omega t times what? You tell me. Exactly, f double prime. The second derivative of f. So e to the power I omega t will cancel, and you will get an ordinary differential equation in f. You solve that. Okay, and that's what will give you the solution for y, an exponentially decaying solution for y. That's your f. So you plug back that f and then satisfy the two boundary conditions, okay, at y equal to 0 and y equal to infinity. And then you will get the two integration constants. You need to go through that process. This is again ordinary differential equation with constant coefficients. So you should be able to solve that. Okay. So does that put you on the right path? Okay. You need to complete it though. Any other questions? Yeah.
How did you go from the V naught cosine omega t to V naught e to the I omega t? From like the yellow
to the green
highlight to the green highlight.
Yellow highlight is the boundary condition. It's a boundary condition that is given at y equal to 0, which says that the bottom plate is moving with a periodic boundary condition. That's given in the problem. But that's the source of inspiration for me to suggest that the separation of variable solution that I'm proposing is going to have not only this form, a function of time times a function of y, but the function of time must be a combination of sines and cosines. Okay, and that's why I propose e to the power I omega t. That's a proposition, meaning I'm conjecturing that the solution must look like that. Okay, because the boundary condition looks like that. If I don't know that, then I will have to actually leave it as some function of t and then do the separation of variables. and I will get two differential equations, one in time and one in space, like we did the last time. And when you integrate the time equation, you will discover, even though it may have many functions that satisfy that equation, this is the only one that will also satisfy the boundary condition. Okay? And in an exam, I don't expect you to come up with this conjecture. So I will tell you, take a solution of this form and then proceed further. Because that comes only with experience. If you do a lot of problems, you have seen enough problems, you'll say, okay, I'm going to try a solution of this type. But you are just learning now, so I will give you that help. Any other questions? Remind me when it is 4:45 or so, because sometimes when I keep talking, I forget passage of time. Okay, so we have seen so far one-dimensional problems. That is one velocity component that is changing in only one spatial dimension, plus time also. Okay, both steady and transient problems. Cuvette flow, puzzle flow, in plates, in cylindrical pipes, concentric cylindrical pipes with angular velocity or with axial velocity. All these combinations you should be able to handle. Okay. Now we are going to switch, and we will do this going back and forth. We are going to now, because the mathematical apparatus is the same that we need to solve heat transfer problems. This is from chapter 10. So we derived the momentum equation and the energy balance equation and the mass balance. We didn't derive the mass balance, we wrote it down by analogy. Okay? So we can just draw on these equations to be able to learn to solve the same classes of problems in heat and mass transfer. Because this course is transport phenomena, we want to see the unity in all these three transfer processes. So the problem that we are going to look at is, again, an idealized problem, one-dimensional conduction heat transfer. And then we will extend it to convection heat transfer. So what you have is an infinitely long cylinder, a solid cylinder. Think of it as a wire, copper wire or aluminum wire, that is carrying a current through that wire. Okay? What happens as the current passes through it? There is some resistance. So there is some...
Solid?
It is completely solid. This entire thing is solid. What he is showing, I've taken this figure actually from Burstiever and Lightfoot. What he's showing is how to make the shell balances. And we have stayed away from shell balances because we have derived all the equations. He's going to show you how to derive this equation for an energy balance, how to solve it. I'm going to focus on how to solve it only, because our approach is, I've derived the equation in the most general three-dimensional form in the three Cartesian, in the three reference frame, Cartesian, cylindrical, and spherical. I have access to that, so I can take that equation and go through this process of cancelling all the terms that are irrelevant for a particular problem. Simplify the equation, write down the boundary condition, solve it, and analyze it. So this one he shows using a shell balance. That's why you see this, but it is supposed to be a solid wire, okay, a solid copper wire or aluminum wire or whatever. But there is current flowing through that, and that current creates some heat, resistive heating. Okay, I square R losses kind of a thing. So that heat is generated uniformly in the entire cylindrical rod. But it is such a long, infinitely long rod that the heat that is generated is going to be moving from the center towards the outer radius and then going out to the surrounding. Okay, so the surrounding wall is maintained at a certain temperature, and the heat is going to be removed from that outside wall at a certain rate. The question is, what is the temperature profile going to be in that particular system? Do you understand the physical description of the problem? You have an infinitely long wire, and our task is to find the temperature, the flow, the heat transfer steady, okay, and there is a heat generation. There is heat generation. There is a source term, a source for heat, which is the resistive heating due to the current flowing through that. So if you take any elemental volume here, what you're saying is that there is heat coming into that by conduction, there is heat leaving that other surface by conduction, and there is heat that is being generated within that control volume. These three should balance. Okay, but in our case, what we are saying is that this temperature variation is going to occur only in the radial direction, and there is no variation with respect to time because it's steady state. There is no variation with respect to axis because it is infinitely long, and there is no variation in the theta direction. Why? Axis symmetry. Okay, so it's a function only of r. T is a function only of r, so we are assuming axis symmetry. So it means there is no theta dependence and infinitely long. No z dependence, and it's steady, that means no time dependence. Our task is to find that function under these conditions. So I need to tell you what is the rate of heat generation. So it's a cylindrical coordinates. This is in your formula sheet. This equation will be in your formula sheet. This is the equation for energy transfer by conduction, convection, and heat generation. Okay. So on the left hand side, if you look at it, it is the Lagrangian derivative, the substantial derivative. So we are saying that there is no variation in time, so that's 0. And is there Vr, V theta, Vz in this problem? There is no velocity. It's a solid. There is no velocity. Okay. So Vr is 0, V theta is 0, Vz is 0. Okay, so the entire left hand side is 0. On the right hand side, we just said that the temperature is not changing in the z direction. It's not changing in the theta direction, but it is changing in the r direction. What about the last term? It's a source term, but in this case, it is a viscous heating. So only when there is a flow, the friction in the flow due to viscosity will create that term. In our case, it doesn't exist. In the next problem we are going to do, it does exist. Okay, we'll come back to that. But for this particular problem, that is equal to 0. But there is a different source, that is the electrical heating. Takes the same role as this source, but the form of the expression would be different. Whereas in this case, it will depend on the velocity profile, the viscous heating. Whereas electrical heating will depend on how much of current you are passing through and what is its resistivity. Okay, so that's we are going to call as SE. SE is the volumetric heat source, which has the units of so many joules per meter cube second. That is that so many joules are created for every meter cube of that rod, of that wire, per second.
The term you cancel out as 0, the final term, that's a source term, right?
That is also a source term. It will have the same units, yeah.
Yeah, but like you said, there's electrical heating. So you're replacing that with SE.
Right, right. The form of the source is different. The reason for the source is different. But the source term will always be a term that is added in the energy balance equation. What are the typical...
Is that one like a really general term, or?
No, in this particular case, this is a very specific source term, which is the viscous heating. That's why it is written as mu times 5. Mu is the viscosity.
Okay, that's viscous heating.
That is viscous heating. What are the causes of source that you can think of? What are the mechanisms that generates heat? Obviously viscous heating, friction, electrical one that you talked about. Can you think of anything else? Radiation. Anything else? Chemical reaction. So if you have a catalyst pellet, a cylindrical pellet, and there is a reaction taking place, there is heat of reaction, right?
So they're all like different.
They are all essentially taking this place, but the form of that will depend on what is the mechanism that generates the heat. Okay, and nuclear heating, for example, in a nuclear reaction, the fuel rod that is made up of cylindrical geometry, there is a nuclear reaction that can create some heat for you as well. Okay, and there is an example in Bird, Stewart, and Lightfoot where he talks about both chemical reaction and nuclear reaction as sources. He also talks about viscous heating, which I'm going to do, but the remaining two I won't do. But you will be responsible for handling all these variations. Okay, any questions? Okay, so SE is the volumetric heat source, meaning it's distributed uniformly throughout the volume. Okay, so it has the units of joules per meter cube second. Look at this equation. What does this equation remind you of? Instead of T, if I put a V, how does that equation look like? The equation for velocity profile in a pipe flow, the Puzzle flow in a pipe we derived, we should compare that equation. It has exactly the same form. If T is replaced by the velocity, and the source term SE is replaced by what? dPd is at the pressure gradient. So the pressure gradient is like a source term, external forcing term that causes the movement of the fluid, the velocity. Okay? In this case, it's the heat generation that is causing the temperature profile. So if you look at the mathematics of this equation is exactly the same as that Puzzle flow equation. If you make these two connections, T is taking the role of V and SE is taking the role of dPdZ. So what would you expect the velocity profile to be? You need to remember what it was for Puzzle flow. Parabolic. That's exactly what would happen. Okay. And does that make sense? Why should the velocity profile be parabolic? So what we are saying is, if I plot T, this is for example some temperature T0 on the surface. I'm maintaining the outside surface exposed to room temperature T0. Inside, the maximum is going to occur at the center. Does that make sense? That's because that plane would be axis would be an axis of zero flux. The temperature gradient is maximum. So what is temperature flux Q? According to Fourier's law, K times dt dr. So dt dr at this point will be 0. Okay? So the temperature is maximum, just like the velocity was maximum in the previous case. So the heat is going in the direction of the gradient of the temperature from the inside to the outside. It's uniformly produced everywhere, but the only way it can get out of the control volume is through the outer surface. Okay, so that outer surface happens to then reach its lowest temperature. From there, it will build up. And of course, when the temperature gradient everywhere is 0, of course, there is no heat conduction. So physically, you can understand that this is reasonable. Mathematically, you can look at the similarity between this and the Puzzle flow. What are the boundary conditions? The boundary conditions, as I said, at the outer boundary at R equal to R, the temperature is T0. Think of that as the ambient temperature, room temperature. Okay? And at the center, dt dr equal to 0, the symmetry condition. Again, the mathematical analogy is exactly the same, because we had, what did we have for velocity at the outer boundary? 0. So if you define a new variable theta as equal to t minus t0, you can put them in dimensionless form. Then you will get the excess temperature to be 0 at the boundary, if you want to make the analogy even more close. Okay. Now, integration of that differential equation is something that I expect all of you to be able to do, because it is a second order ordinary differential equation in cylindrical coordinates. You should be able to just separate and integrate twice, or put the characteristic equation and solve it, whether it is Cartesian, cylindrical, or spherical coordinates. So I'm going to give you the same problem in a sphere. There is uniform heat generated inside a sphere, and there is conduction. So the idea is going to be exactly the same. The only thing that will change is, instead of going into cylindrical coordinates, you will look at the spherical coordinates and simplify that, and you will still get an ordinary differential equation, which will look different. And you should be able to separate, integrate, and get the solution out of that. Okay, so integrating once, you get S over K. That is, I'm moving the K to the right hand side, and then you'll get R dr, so which becomes R square over 2 plus an integration constant A1. Then move this R to the right hand side and separate and integrate one more time. So that's going to give you minus SC over K. Again, when you divide by R, this R square will become R. So you'll have R dr one more time. So when you integrate, you'll get R square over 2. Another 2, that makes this 4, plus A1 times dr over R, which will give you the log R. Okay. and then A2, second integration constant. And for the same reason as before, at the center dt dr equal to 0 when r is equal to 0. So A1 is going to be equal to 0, the symmetry condition. Another way of looking at this is if I let A1 to be not equal to 0, then I get into difficulty because logarithm of 0 is minus infinity. It's not defined. Okay, so that gives you a nonsensical solution. So I cannot allow even though log r is a function that satisfies the differential equation, it doesn't satisfy the boundary condition. So you throw that out. Okay, so the only solution then would be r square and then a constant. So impose the other boundary condition and solve for a and b or a1 and a2, and you get your solution like this: a parabolic or a quadratic temperature profile. Now you can ask questions. Okay, what is the maximum temperature at the center? All you have to do is put r equal to 0 and you get your T max. What does it depend on? It depends on the thermal conductivity, of course, right? The larger the thermal conductivity, the lower the maximum temperature. What does that mean? If it's a good conductor, it's able to dissipate the heat very quickly to the outside. So the temperature rise will not be as big as it is. Okay, so that's why it appears as n inverse. But it's directly proportional to how fast you are generating the heat. That is SE. So if SE is very large, that means you are generating the heat very quickly. You're not able to transfer it out because K is small. Then the temperature will shoot up in the middle. Okay. Where can you use problems like this? Suppose you are designing a fuse. You know what a fuse is in an electrical line, right? What does that do? Breaks electrical contact, right? So it's a safety device that should melt. The fuse should melt if it's drawing a current above a certain value. So if I ask you to design a fuse for carrying certain current capacity, 5 amps, through a circuit, this equation could come in handy. How would you use this equation? You want to find, for a given load,
SE will be defined by the current and the
exactly. SE will be defined by I square R, that quantity. Okay, and once you know that, what is the current capacity, you know SE, and you can immediately find out what will be the maximum temperature, right? So you want this to fail at a certain current capacity or a certain value of SE. What do you need to do? You need to find a metal that has a melting point that is low enough so that as soon as it reaches that maximum temperature, it will melt. That's how it breaks the circuit, right? So that's how you can find applications for simple equations like these. The next one is answering the question, how much of heat is being transmitted from the surrounding surface in the radial direction? What is the total amount of heat that is being dissipated to the surroundings? What do you expect that to be intuitively without solving this differential equation? Whatever, under steady state condition, whatever heat that you generate in the pipe must be transferring out. There is no accumulation, right? So you can simply take SE multiplied by the volume of that material, and that should give you the amount of heat that you dissipate. That's what it in fact says, SE multiplied by pi r square L. Pi r square L is the total volume of your cylindrical pipe. Okay, so that is the total amount that is produced, and that must be dissipated. But what we are saying here is I can calculate that amount by knowing the temperature gradient at the wall, because the Q that comes out of here is going to be equal to minus K dt dr evaluated at R. That is, on that surface, on the cylindrical surface, I am asking the question, how much of heat is leaving that cylindrical surface? Okay, so that's going to be equal to Q at R, the flux, heat flux at R. What is the units for heat flux? So many joules per meter square. It's a flux, right, per meter square second. Okay, so I need to multiply that by the surface area. The surface area for the cylindrical shell is 2 pi r times L. Okay, so this is the surface area, and you multiply it by the flux, and of course, you need to evaluate the flux. That means you go to this expression and calculate dt dr. And put, after you take the derivative, put r, lowercase r equal to capital R. And that's how, like minus k times dt dr, and then substitute, and you will find that you get exactly the same expression, which we kind of intuitively argued that it should be the volume times SE, but you will get exactly the same expression through this way. So that basically shows that heat balance indeed is satisfied, no matter how you calculate, in terms of looking at how much of heat is leaving this volume or how much of heat is produced inside the volume. They should both be same under steady state condition. Okay, any questions? This is easy, right, compared to separation of variables and similarity transformation. No questions? Okay. Let's do the last problem. This is from section 10.4 in Burstsever and Lightfoot. This is an interesting problem. This has viscous heating now, but you need to understand. Let me describe the problem to you physically, and let's see whether we understand what he's talking about. It's a problem of flow between two concentric cylinders, problem that we already solved. Okay, so you have an inner cylinder here, the inner cylinder, and then there is the outer cylinder. Okay, and in between that I have a viscous fluid, and the inner cylinder is at a temperature of T0. The outer cylinder is at a temperature of TB. The inner cylinder is fixed and the outer cylinder is moving with an angular velocity of omega, and hence its angular velocity is so many radians per second. So the outer one is spinning at an angular velocity of omega, so its linear velocity is omega times r. R is the radius to the outer cylinder. You understand the description so far? Now, if I put a very viscous fluid, and this is often happens in lubrication problems, when you have two ball bearings that are close to each other and you have a lubricant and they're spinning, it's going to create a lot of heat. Okay, what is the cause of the heat? Viscous desiccation. Okay, so what we are going to do is we are going to analyze this problem in the limit of very large radius and very small gap. The gap between the two cylinders is B, and B is very small. Okay, so I'm going to ignore the effect of curvature. So I'm going to it is exactly like two parallel plates. So I'm focusing only on this zone. So it is as if I'm stretching it out. So if I cut this and look at it, so it looks like the bottom plate is fixed, the top plate is moving with a certain velocity, which is omega times r. The bottom plate is fixed. Okay. Now, I might ask you to do an analysis on the cylindrical geometry, but I'm showing you the analysis for a flat plate geometry. So, physically, do you understand what is happening? So, what is the velocity profile for that problem? It's linear. We already know that. We have already solved that problem. This is the Couette flow. The bottom plate fixed, the top plate moving under steady condition. We have actually studied transient one also. This is under steady condition. Okay. So the velocity profile is linear between the top and the bottom, and it's probably worthwhile to note what is the relationship between the cylindrical coordinates and the Cartesian. In cylindrical coordinates, we have r, theta, and z. Okay, so from this figure, which coordinate corresponds to r? X. Because r is in the radial direction as you go out. Okay, so and that gap is b in our case. So r is the same as x in the Cartesian plane. What would be theta? Theta would be z. So it's as if you are moving in this direction. That's theta, but that's the same as moving in this direction. So what would be z in the cylindrical coordinates? Would be perpendicular to the board. So that will be something like y. If you make that connection, then you can interpret the results in terms of what happens between the Couette flow between concentric cylinders. But what we need to do is take the equation in Cartesian frame and try to simplify it. So we know that the velocity profile has Vz as a function of x, remaining for 0. What about temperature? It's going to be a function only of x. That means there is no variation in the z direction. What would you call that condition in the cylindrical case? Axisymmetry, right? That means whether I take in this plane or in this plane or in that plane, the velocity profile is the same. As I go around the axis, the center of the axis, it's the same. Okay, so in the Cartesian frame, you would call that as a fully developed condition. There is no variation in the z direction. In the cylindrical one, you'll call it as an axisymmetric case. Okay, so we already know the velocity profile. The velocity profile is Vz as a function of x. Do you remember what it should be? Vb times x over b. It's a linear profile in the x direction. Okay, so at the bottom plate when x equal to 0, the velocity is 0. At the top plate when x equal to b, the velocity is Vb. Okay, so this we already solved, and you should know how to solve that. So we're going to focus on the temperature. Subject to this assumption, so it does not depend on time. And do we have Vx? There is no Vx, right? Do we have Vy? There is no Vy. Do we have Vz? We have Vz. Can we throw that term out?
Yes.
Very good. Why?
Because t is a function of x.
T is not a function of z. Okay, so you're ready for the exam. If you can do this, that's the main thing I'm going to look for. Given a description, you should be able to simplify it, write down the boundary conditions, stuff like that. 50% of the job is already done. On the right hand side, what do we have? D square t dx square. T is a function of x, right? So you must have that. So that will remain. How about in the y direction? Z direction. Okay. What about the last term? That will remain because that is the source of heat now. Okay. And it can turn out to be very small. Viscosity is very small. For example, I have this rotating thing, but I have air in between. Air is not very viscous, so it's not going to generate a lot of heat. But if I put a lubrication oil in between with a viscosity of 1000 centipoise or something, then the heat generation can be significant. And what we want to do is predict what will be the temperature profile under this.
So if you give us something like the fluid is air, can you just like under the assumption that the viscosity is?
Yep. Okay, so now I'm not going to neglect this because I haven't told you what it is. Okay, so we are going to include that. And what you need to do is that expression for the viscous dissipation is a pretty long, messy expression. But we saw already that it is a positive definite function, meaning it's always a source term. It can never be negative. And if you notice, all of them will have square in it. If you're squaring any number, it's going to be positive, right? Any number inside negative is going to become positive. So 5v will always be greater than 0. So you need to examine every one of these terms and see which one is not going to be 0. How about Vx with respect to x? 0 or not 0? Remember, we have only Vz as a function of x. All the others are 0. You can imagine in a truly three-dimensional flow field, all these derivatives will be non-zero. Okay, that's where you need COMSOL because we cannot do it by hand. So we let the computer do the solution. But now we can do it. So this is going to be 0. Vy is going to be 0. Vz with respect to z is going to be 0. And Vy with respect to x, 0. Vx with respect to y, 0. Vz with respect to y, 0. Vy with respect to z is 0. This is Vx with respect to z and Vz with respect to x. That will survive. Okay, and then if you look at this is nothing but continuity equation. Okay, Vx with respect to x is 0, Vy with respect to y is 0, Vz with respect to z is also 0. So the only non-zero term from that such a complex, messy term is Vz with respect to x, but it is squared, so it's a positive term. Okay, so the energy equation simplifies to this non-zero term, and out of this non-zero term only that one survives, and that's what I get. Now, what is the difference between this problem and the previous problem where we had electrical heating?
The source was constant, here it's function.
Exactly, the source was constant in the previous case. It's uniform everywhere in space. Here, the velocity gradient, it turns out that it is constant. Why is it constant? Because the velocity profile is linear. When you take the gradient, it turns out to be constant. Okay, but in principle, the heat generation can change from point to point depending on how complicated this expression is. Okay, so it's a term with a source that is varying with position in general, in principle. But in this particular example, once again, it turns out to be constant because Vz is given by this simple linear profile. Okay, and so when I take the derivative of Vz with respect to x and I put it back in there, okay, so I get Vb over b. Now I need two boundary conditions. The boundary conditions are at the inner boundary the temperature is T0, or the bottom boundary it's T0, and the top boundary it's Tb. Both are known. I'm maintaining these two surfaces exposed to those temperatures. So what I do is I take this and plug it in there and then simplify that to the following equation. K times d square T dx square plus mu times Vb square over b. So everything here is a constant. Mu is a constant, Vb, rotational speed, is constant, and the gap is a constant. So it turns out in this case also it turns out that it's a constant uniform source. When can you even in this problem, and there is an exercise problem in Burstever and Lightfoot that he talks about, and you should understand that. But let me just pose the question. If viscosity is, does viscosity change if I change temperature?
Yes.
It does. Okay, particularly for viscous fluid. If I take oil, crude oil, for example, you heat it up, it will flow much more quickly. The viscosity is a very strong function of temperature. How would this problem change?
Mu will be then a function.
Mu will be a function of temperature. What does that do to the velocity profile?
The velocity will increase depending on the type of
So the velocity profile will be influenced by the temperature profile, because the temperature profile will influence the viscosity, and the viscosity will influence the velocity profile. So we would call that kind of a problem as a fully coupled problem, because velocity influences temperature, temperature influences velocity. They both depend on each other. That means the two equations, for example, the energy equation has viscosity and the velocity there. Okay, the gradient of the velocity. So the temperature will depend on that. But if you look at the momentum equation, what was the momentum equation like? It is mu times. Actually, I cannot take this outside the derivative. Something that you should be aware of. I will have d dx of mu dv z dx. That is the momentum equation. For a case where you still have a coed flow, one-dimensional flow, but mu is a function of temperature. You can integrate this once, okay, but the second integration is going to be difficult because you don't know what temperature is. Okay, so you would call that kind of a problem a fully coupled problem where each variable affects the other variable. So the two equations must be solved simultaneously. But what are we doing here? Here we are solving the velocity equation first, because if mu is constant, that can be solved. It is not affected by temperature. And then take that result, plug it in here, and then you can solve it for the temperature profile. So that variation you should be able to, there is an exercise problem in Burstever and Lightfoot that you should take a look at. Okay, that's what we mean by two-way coupling. Both equations are influenced by the other equation. They're completely coupled. Here it's one-way coupling. which is the way the coupling goes. Velocity affects the temperature, but the temperature does not affect the velocity. Okay, do you understand the idea?
This is an assumption you made.
It's an assumption about the nature of viscosity. So if the temperature change is not significant between, that depends on what is the difference between TB and T0. If that difference is small, that means you are maintaining a small temperature difference. Okay, then it may be reasonable to assume that the viscosity is constant over that range.
TB is larger than T0.
That you control. You can control it because these are boundary conditions. So you can maintain by putting an ice pack on the inside or the outside. You can maintain it at whatever temperature you want. So whichever surface has a lower temperature, more heat will go through that surface. Heat that is generated inside between the two plates, which one will take more out? That depends on which one has a lower temperature. That's a good way to look at it. Okay. So once again, we have a constant coefficient, second order ordinary differential equation. So integrate it twice, separate it, and you will get this as the solution. It's a fairly straightforward separation and integration. And you will have two integration constants. And you already have two boundary conditions. Okay. So impose the boundary condition, you'll get C2 as equal to T naught. That is at the lower boundary, x is equal to 0. So T is equal to T naught gives you C2 equal to T naught. Okay. And at the upper boundary, T is TB, but x is B. So you have to substitute for B. X squared becomes B squared. So that's a little bit messy equation. So you need to extract C1 out and move everything else to the right hand side. And then put back the two integration constants. And I'm doing a little bit of algebraic manipulation. So when I say in an exam, show this, you should be able to go through this intermediate steps. For example, here what I'm doing is I'm moving this T naught all the way to the left hand side. So I'm writing it as T minus T naught. Then I'm dividing every term by TB minus T naught because I have TB minus T naught here. Okay, and what I will get is this expression that you see here. Dimensionless temperature on the left hand side is equal to a quadratic profile because it's x squared over b squared, x over b. So x over b is your dimensionless position. Okay, and so what do you think this number should be? What are the units of this number? Also dimensionless, because everything else in that equation is dimensionless. And that number is called the Brinkmann number, in honor of the person who studied this problem first. Okay, it's a dimensionless number. What is the physical interpretation that we can give? It is the ratio of the rate of heat generation due to viscosity in the numerator, and that appears here, and the rate at which heat is conducted to the two sides, which is in the denominator. K, the thermal conductivity times the temperature gradient, TB minus T0 between the two walls. Okay, so it's a competition between those two. So when Brinkmann number is small, what does it mean? Dissipation is smaller. It's not creating as much heat, and it's able to conduct whatever it creates very quickly. The denominator is large, numerator is small. When Brinkmann number is small, the numerator is small, the denominator is large relatively. That means conduction is very effective. So you have a high conductivity fluid maybe, but not a high viscosity fluid. So it's not generating as much heat. Whereas the Brinkmann number is large, it means it's putting out a lot of heat because of friction, it's not able to conduct as much as. So that will result in a higher temperature in the middle. So if Brinkmann number is large, the temperature T is going to be large. It's proportional to the Brinkmann number. So if BR goes up, T goes up. BR goes down, the maximum temperature in the middle. Remember, this is a parabolic profile, but a funny parabola. Not symmetric. Why is it not symmetric? Because we kept the two boundaries at two different temperatures, TB and T0. What would happen if I take TB to be also equal to T0? Then it will be parabolic, right? Right? That's what you would expect intuitively, right? And you should be able to show that. So because you have the more general result, now you say what happens when I take T0 in both. Then I see it's again a parabola, still a parabola, but different parts of the parabola. Okay. So this is the problem I want you to study, which talks about viscosity dependence on temperature. Take a look at it. Okay. That was perfect time. 4:45. I wanted to finish, and I finished it. Okay. Any questions?